Now, another phenomena is fatigue failure. What is fatigue? It is a type of failure that occurs in structures subjected to dynamic fluctuating stresses. Means the stress might change from tension to compression, compression to tension back. So, these kind of fluctuations might happen in the stresses, and that leads to a failure phenomenon called fatigue failure, and this is widely observed in metal structures. About 90% of the failure of metallic materials is due to fatigue. Okay. A very important phenomena when we look at metal structures. So, in case of civil engineering, we have bridges. Definitely there are steel bridges, steel structures, but the steel bridges are more prone to fatigue failure because bridges are used for vehicles. So, you have moving loads on the bridges, like vehicles when they pass, it's like vibrations are induced onto the bridge structure, and that can lead to this kind of fluctuating stresses which lead to eventual failure. So, here are some examples showing how some demonstrations on fatigue related distresses on the bridges. You can see here on the top left, this is the bridge. Over here you can see the steel truss over here, and this figure is the top view of the same bridge. It is in Minnesota I-35 bridge, which collapsed due to fatigue related failure, and also some people say there were lack of redundancy in the structure. But let us focus here on that fatigue, because there are reports which says it is due to fatigue failure. And you can see another example where there is a 7-foot long crack on a bridge, you can see here. Okay, it is a steel girder. Here is another example where there is a crack on the, here also you can see another crack on the steel members, and here is another crack which you can see on the steel member. So, there are many steel bridges which are vulnerable for to fatigue failure. And also other industry, when we look at aircraft, machine components, all those also experience severe fatigue related distresses. Now, what are these load, where we just talked about variation in the stress from compression to tension, tension to compression. In general, we can classify them as 3 type of cyclic loading. One is reversed stress cycle, where you can see the first graph on the top, where it is symmetric in nature along the, this is the axis. So, it is symmetric in nature, and that means this height is same as this height here. Okay, the amplitude is same both for compression and tension. You can see the above the graph it is tension, and then here it is compression. Okay. Now, for the next case, repeated stress cycle, here it is not necessarily symmetric like the above case. You can see the graph center line is here, or the the zero stress line is here, and then you have compression here and tension. So, you have more tension in this particular case than the compression. So, that is another case. And the third case is random stress cycle, which is probably the most common in case of civil engineering structures. Okay, because most of our loads are not well defined. If you are talking about a bridge, you cannot really well define the type of load, the actual load which is coming on to this particular truss element, because that depends on the type of vehicles, the weight on the vehicle, many factors play a role on that. But still, for design purposes, we try to design by using 3 parameters, which are mainly the average of the stress, then amplitude of the stress, and the range of stress. So, these 3 parameters we consider for design purposes, and by approximation of the loads which are coming. So, you can say here this will give me the range of the load here, and then maybe I am able to model, if I can model this load pattern and then try to fit it to some kind of equation and model it nicely, and then you can be used that kind of model, and the corresponding 3 terms like the average and the amplitude and the range of stress can be used. So, here in the second case I will show you what is the average. So, this is the average line here, okay, and this is the amplitude for the compression, and then you have this is the total range of the maximum compression and maximum tension. So, all these parameters can be used to design the structures. Now, let us see what is the mechanism which is happening when you talk about fatigue failure. So, you can see on the top right I replotted the same graph which we used earlier. So, assume that this is the stress strain graph, and then fatigue failure can happen at a lower stress level than the actual ultimate tensile strength or compressive strength of the material. Now, you can see here under fluctuating stresses, it is possible for a failure to occur at a stress level lower than the tensile or yield strength for the static load. We are focusing here tensile strength here. So, this can happen at this condition here. That means, even if the stress is much below the ultimate is somewhere here. So, only 35 to 60%, let me put this percentage here, 35 to 60 percentage of the load, if it is there is a possibility of fatigue failure to occur, especially in case of steel, typical steel. Now, fatigue failure is brittle in nature. Steel, you can say it is a ductile material, but still when it fails, it can fail in a brittle nature. Here I am showing an example of an aluminum piece which is highly ductile as compared to steel, but still aluminum piece which is broken by fatigue mode, you can see that there is no really flow of the material here, and it just broke into 2 pieces without really deforming like in usual case. The necking and all that is not happening here. If the same aluminum piece is pulled in a tensile strength test, you might probably see necking and then cup and cone failure, but here you are not seeing that. This is because it is a fatigue induced failure. Okay. So, the total plastic deformation associated with the failure would be very, very less, even if the material is ductile in nature. Now, how would the fatigue failure happens? There are 3 stages for this. Stage 1, crack initiation, that is this here, it happens right here, okay. And then stage 2 is crack propagation, which happens for up to this much distance, crack propagation, and then the remaining portion is stage 3, okay, or the final failure. Now, if you look at the time taken for all these, initiation, of course, it just happens when there is a small crack or something which is happening, but the crack propagation period, that will be very long as compared to both the first and third case. You will have several cycles to undergo before, all these lines over here indicates 1 by 1 cycles, cyclic loading, okay. So, which could be in millions, here it is demonstrated with very easy to see as lines, but there could be millions of cycles or millions of those crack propagation steps. And then once it reaches some threshold level, then the remaining material fails all of a sudden. This happens all of a sudden very quickly, okay. So, that is the final failure, the third step. Here is an example for that. You can say this initial crack happened here, and then here you have the propagation phase, and then from here onwards it is all of a sudden the final phase, okay. So, here the smooth region you can see on the top, that is the this region here is the initiation and propagation region, and then this is the third phase here, the darker color region. Now, if you look in microscope, through a microscope, you can see the same pattern. You see like this over here, this pattern, and here also you can see striations depending on the microstructure and the type of loading which the material is experiencing. All these small lines, I draw it very You can see a lot of these narrow small lines here. So, that indicates each loading cycle or a small failure propagation of the failure under each loading cycle. Okay. So, and they also call it beach marks or clamshell marks because it looks something similar to that. Okay. So, he can see here. Anyway, so in microscope when you look at, you can probably see a lot the millions of cycles, that the evidence that it does not happen in just few cycles of loading. Now, how do we take care of this problem in our design? When we design structural systems, knowing that there will be cyclic loading, how do we handle that? Okay. So, there is something called SN curve. S stands for the stress amplitude and the N stands for the number of cycles until failure. Okay. Now, you can see two curves here, one is a red curve and another one is a blue curve. One for the red curve for the most non-ferrous materials and the blue one or dark blue for the ferrous or titanium alloys. Okay. So, let us first discuss the ferrous or titanium alloys and then we will go to the non-ferrous material. So, some ferrous and titanium alloys becomes horizontal at higher N values or higher, the more the cycle it becomes horizontal. You can see this here, this graph over here, it is more or less horizontal after about 10 to the power of 6 cycles. So, from here it is horizontal, right. Now, that is a very good property which the ferrous or titanium alloys have. That limit or the corresponding stress value SE, which I am calling, or endurance limit or the fatigue limit, it is a stress below which failure due to fatigue will not occur. Okay. So, it is a good thing because if our stress level, if the stress level acting on the material is going to be less than SE for that material, for less than SE, then you do not have to worry about fatigue failure, because no matter how many cycles you have, it is still going to be flat. This curve is going to go like this. So, there is no fatigue failure if the applied stress is going to be below the endurance limit. Okay. That is one thing. Now, let us talk about the non-ferrous materials. Here there is nothing like endurance limit or fatigue limit. Let us look at the red dot dash arrows there. So, I am going to start from N1. Okay. So, I go upward and I hit the red curve, let us say some non-ferrous material, and now I go leftward and I reach here, and that is the fatigue strength, which is the stress at which failure will occur at a specified number of cycles. So, my specified number of cycle in this case right now I am discussing is N1, and that means the material will fail when the stress is here. Okay. That means about let us say there is no unit on this. So, let us say this point A I am going to call, or I am going to call S1, N1 and then S1. Okay. Or S0, because I have already another S1. So, now look at the green. So, this is the case where I am in a design stage, where I know what is the number of cycles which the structure is supposed to, number of load cycles which the structure is supposed to experience or supposed to withstand for. That is N1, and the corresponding let me S1 itself is better, corresponding S1, okay, or the stress corresponding to N1. Now, what I have to do as a designer is that the stress which is going to be experienced by the material should be kept below S1. As long as I do that, the system will survive for n1 cycles. That is the idea. Okay. So, the load, applied load has to be less than S1. Load applied has to be less than S1. This is the design stage. Now, let us say you are talking about a bridge or any structure which is already built, and you now you want to see maybe there is an increase in the load or something. So, you want to assess the remaining life of the structure. So, what do? You know the stress which is applied, that is known. In the green case here, the stress is known, and I look at the change in the direction of the arrows. Okay. So, you go from here you go to the right and hit the curve and then come down. That is about 10 to the power of 6 cycles. Now, what we have to do is, if this is the load which is applied, let us say stress which is applied, SA I am going to call, or S1, S1 is, or S1 or SA, whatever, does not matter. So, I am going to make it S1 itself, so that there is no confusion on that. Okay. S1, now it comes here, the green text here, it is saying fatigue life at S1 stress. So, that fatigue life is 10 to the power of 6 or about that. Now, I can say how many cycles the structure has already experienced and what is remaining cycle, because I know that if the current load is being applied, it will not stand beyond 10 to the power of 6 or approximately that. So, as a person who is in charge of that, if the structure the life of the structure need to be extended, what you have to do is, you have to reduce the S1, okay, you have to reduce S1 and probably start somewhere here and then go further and then make sure that it gets more life. So, this is the use of this kind of graphs. We can design the structure to resist fatigue load, and also we can design the retrofitting strategies to ensure that the structure really meets the new demand also. So, you might sometimes want to reduce the size, increase the size of the column. Let us say there is a column which is originally of this size, and now you have to reduce the stress a little bit. What you do? You put additional column, so that the entire load which is coming is going to be half, because the total load P is same, right. Now, P divided by area is the stress. So, in stress in 1 and stress in this case 2, stress in case 1 means only one of this column, and then stress in case 2 will be 2 columns. Okay. Now, when you double the area, definitely the sigma 2 is going to be less. So, that means we can actually increase the life by reducing the stress applied. So, this is the whole idea. Okay. Now, these are some examples of SN curves. This is for steel. You can see this flat region here, and then you have alloy which is going down like this, and you have nylon which is also going down. Okay. So, looking at these curves, we can decide what is where we can use these curves both for design purpose and for analysis and life extension purposes. Okay. So, we just discussed like very simple graphs, right, but when in reality, when we actually do this test on various materials, there is a lot of probability which comes into the picture. As you see on these graphs, you can see here in the green one, there is this variation, there is this variation, here you have this much variation, okay, and in the red one you have this much variation, this much variation, this much variation, you can see here. So, how do we handle these variability in the test results? So, we can look at the variation at every point and then draw some probability based curves. So, I am going to show you that in the next slide. So, probability based curve. So, for example, here I can say this is probably the mean value, and then the graph is going something like this. That is what I draw here. So, there is a mean value associated with the data and then also the probability or the scatter. Okay. Now, these are graphs made based on the type of data which is obtained previously, like in the previous slide. Then you draw these different curves associated with different probability of failure 0.99, 0.9, 0.5, 0.1, 0.01. Okay. So, I have 5 curves here indicating different probability of failures. Now, focus on the blue dash lines. You can see the look at the horizontal blue line. Okay. Now, that I know a corresponding stress is 200 megapascal, the stress corresponding to the horizontal blue line. Now, I have to see what is the number of cycles at which some probability of failure can be defined. So, for example, if the system reaches about a little bit more than 10 to the power 10 to the power of 6 cycles, if when n is equal to about here, the probability of failure is 0.01. Okay, I am talking about this point here. If the number of cycles is here, then probability of failure is 0.1. I mean the second curve here, this point. Like that, I can find the probability of failure corresponding to different cycles, different number of cycles or load cycles. So, when it reaches that particular load cycle, I know that how seriously I should take care of the repair activities or other maintenance activities or retrofitting, so that I can still bring the probability of failure down. Okay. Now, look at the red dash lines. I am going the other way, where I am putting one cycle here 10 to the power of 7. At that time, I can find out at what load, depending on the load or the stress applied, what is the corresponding probability of failure. Okay. So, if I want the probability of failure to be very low, I have to decide on what is that corresponding stress which I can allow. Okay. So, here you can say 10 to the power of 7 and then corresponding point here, and if I want the probability of failure to be very low 0.01, then I have to keep my stress level at this value. Okay. And if I am okay to have a probability of failure of, let us say 0.5, which is not really a good case, but for the purpose of demonstration I am showing that here, the second, the one above. So, then I can go for a stress value of that much. Okay. So, about 30. So, this is the use of this kind of probabilistic SN curves. One thing to note is on the horizontal axis you have logarithmic scale, forgot to tell you earlier. Okay. Now, there are two, when you talk about this variability and all that, I think it is also important to know the difference between standard deviation and coefficient of variation. Average, you know you know that average is mu, which is sum of all the values divided by the number of values, and also standard deviation you have sigma. Now, sigma, or I am going to call it SD here for simplicity, and COV is the coefficient of variation. Now, take case 1 here and case 2 here, case 1 and case 2. In case 1, let us say the average value is 100. I am going to show you here which is more important parameter for you to consider, okay, and why probably standard deviation is not a good parameter to consider always. So, let us say case 1, average is 100 and standard deviation is 10. What is coefficient of variation? It is 0.1, or let us say 10%. Okay, this is equal to 10%. Now, in this case 2, average is 20, okay, standard deviation is 10 and coefficient of variation is 10 divided by 20, that is 0.5, that is this case. So, I can call it 50%. Okay. Now, you can see in both cases 1 and 2, standard deviation is 10, but coefficient of variation is 10 and 50. So, there is a huge difference in the coefficient of variation. So, it is very important to consider coefficient of variation when you want to compare or look at the error or scatter in the data or variability in the material properties, etc. It is very important to consider coefficient of variation and not standard deviation always. You can look at standard deviation if the mean values are also in the similar range. If the mean values, like here, if they are in the widely separated values, then coefficient of variation is probably a better parameter than the standard deviation. Okay. Another concept which is very important is difference between accuracy and precision. Okay. We sometimes get confused with this. So, here look at this thing, four dartboards are here. You can see on the bottom left, low precision, low accuracy, because all these black dots are all over the place. It is widely separated, nothing is close to the center point. Okay. So, that is a case of low precision and low accuracy. Now, here you look at low precision and high accuracy. You see all those black dots are very close to the center point, but not necessarily right on the center. There is still some variability involved in that. So, it is a precision is not very good, but or variability is not very good, but accuracy is very good. Now, high precision and low accuracy, top left, you see all the black dots are very close to each other. Okay, but none of them are close to the center point. So, that is the case, low accuracy, but high precision, all are very close to each other. Now, here the fourth one, high precision and high accuracy, all the points are close to each other and also they are all very close to the center point. So, these are four different cases. I think this is a very easy way of demonstrating the difference between accuracy and precision. Now, in a sketch, a slightly different way, you can see the same thing. When I said precision, I use the word variability. Okay. So, this is kind of the scatter in the data which is available. So, you can see the more the width of this probability density function, this is the probability density function, okay, the more wide the density function is, it is going to be less precision, okay, less precision, the more width. Now, if you are talking about accuracy, it is how far the mean value of the calculated values are going to be from the true value or the actual value, the distance between the mean and mean. Like if you look at the one on the top left, the dot, you can see here the mean of that is very much away from the center point. Okay. So, it is widely separated. So, it is not accurate, but the precision is very good, because if I draw a graph like the PDF on this, it will come something very close like this, it will come. The PDF will look something like this. So, the PDF is narrow or the width of the PDF is narrow, but it is away from the true value. So, the true value is here and these are this thing. So, this is slightly away. Okay. So, you can relate the sketch on the left and right side.